I hope you're enjoying hybrid orbitals as much as I am. It's something that we come back to at the end of the year when we study for the AP test, and sometimes people will struggle with a little, but you gotta nail those VSEPR shapes and bond angles, and if you can really visualize the atomic structure and the orbitals involved, I think that will really help. Often, again, the first thing they're going to ask me for is a Lewis structure. So we've drawn carbon dioxide like a million times, so you might know that it's double bonds. If not, you probably just start sketching it, and then we'll put on some oxygens. And there are 2 single electrons and 2 pairs. That gives me the 6 valence electrons on oxygen. So now you might remember, oh yeah, we'll just link them up twice. And then my other oxygen, I'll kind of line up the single electrons so they pair together. And there's the lone pairs. 1, 2. Cool, double bonds. And again, if you were so good at drawing carbon dioxide that you can just go boom, boom, double bond. Excellent. However, you would not get full credit for this structure yet. Do you see what you forgot? The lone pairs. And I don't know, people must just kind of get lazy sometimes. They're like, who cares? It's double bonds, it shows the bonding. Yeah, but it doesn't show that oxygen has an octet. His other electrons just aren't bonding electrons, but I still have to put them in. Now, technically, you can draw them wherever you want. You can put them on the top and the bottom or on the sides. It doesn't matter in the Lewis dot structure. Either of these would give me full credit for the Lewis structure. Okay, so now they might ask, like, hey, what's the geometry on the center carbon? And I would say linear, right? That center carbon is linear with 180-degree bond angles. There are 2 regions of electrons on that carbon, however I look at it. There are 2 regions of electrons, whether they're single bonds, double bonds, or triple bonds. They'll orient themselves as far apart as possible, which gives me that linear shape with 180-degree bond angles. Okay, cool. So now let's look at the hybridization of carbon. Carbon needs 2 bonding regions. If we need 2 bonding regions, we're going to hybridize 2 orbitals. And magically, we call them Sp hybrid orbitals. Wow, somebody was just creative with this, right? So here again would be my atomic orbitals. Unhybridized. I need the S and one of the P's. We'll hybridize them together, and we'll have 2 equal energy Sp bonding orbitals. These are the hybrids. Anything based on the linear structure needs 2 bonding regions. Oh. That's always this Sp hybrid orbital. That's going to give you the 180-degree bond angles. So let's see what we got going on here. In the carbon atom, in the free carbon atom, we would usually have 1, 2, 3, 4 valence electrons. But that doesn't help me when it comes time for bonding, because we need to show that carbon can bond 4 times. Somehow we want to get 8 valence electrons. In this Sp hybridization, we hybridize an S and a P, and then we're going to have 2 unhybridized. Whoopsie. Unhybridized. P orbitals. Now this is starting to kind of make sense, right? You see some trends. If we hybridize the S and one of the P's, that means we still have 2 regular dumbbell-shaped p orbitals that are still there. They're just unhybridized. And we're going to put 1 valence electron in each of these 4 orbitals. We've got the 2 hybrids and the 2 unhybridized. So here are the valence electrons on carbon. When he's ready to do this sp bonding, hybridized orbital bonding, the valence electrons will be distributed 1, 2. Here's those hybrids. These are 2 different orbitals. I know it kind of looks like a p orbital with the 2 lobes. A p orbital, that's a p orbital. That's considered 1 orbital, even though it only has 2 lobes. These yellow orbitals, that's 2 separate orbitals, the hybrid orbitals. They're 180 degrees apart. 180. And now we got to enter in the 2 unhybridized p orbitals on carbon. And so that's what they're trying to show in blue. Here's one of them. And then here's the other one. Again, they're trying to show this in like 3D. So it's hard when you're looking at a picture in your study guide that's black and white. So the book has these same diagrams and they're colored, so that might help. Or color code them in your study guide if that helps too. So we've got the 2 hybrids and the 2 unhybridized. And again, each of these unhybridized orbitals has a valence electron. We don't know exactly what lobe it's in. It could either be in the top lobe or it could be in the bottom lobe. It could be in this front lobe or it could be in the back lobe. But there would be the 4 valence electrons on carbon. All right, let's see what else we can add to this beautiful structure. Oxygen. Now think about the Lewis structure again. Here's my Lewis structure. Oxygen. Double bond oxygen. Each oxygen I had a lone pair. Cool. Now do you remember that example we just did with the CH2O structure? Now we said be careful of those lone pairs because they need to go someplace. They need an orbital too, right? So around each oxygen I have 1, 2, 3 regions of negative electrons. 1 is a bonding region and then 2 are those lone pairs. But it doesn't matter how I have electrons on the oxygen. If I have 3 regions of any kind of electrons, I know they'll repel and they'll want to go as far apart as possible. That's going to create in here 120 degree bond angles. The oxygens are trigonal planar. And so what they're going to do is say something like, what's the geometry around the carbon? What's the bond angle around the carbon? And I'd say, okay, well the carbon is linear with 180 degree bond angles to each oxygen. If they asked me about the oxygen specifically, I didn't draw these dots, these lone pairs, to the true bond angles, and that's totally fine. I don't have to. Really, it'll look kind of like this. Double bond oxygen. Those lone pairs are at 120 degree angles. So it's really not like they're on the top and the bottom. But again, when you draw the Lewis structure, that doesn't matter. You can put them on the top, on the bottom, on the sides. Nobody cares. But if they ask you for the true bond angles, or they might ask me, what is the angle between the lone pairs, or something like that. Now I really need to think about what's happening around that oxygen. And I have to say, well, there are 3 regions of electrons. Those 3 regions will repel, and they'll orient themselves as far apart as possible. So this is kind of what I'm looking at with 120 degree bond angles. Trigonal planar around the oxygen. So they will specify, if they're asking you about a bond angle or a hybrid orbital or something like that, they'll specify what atom they're referring to. Okay, so now here's a blast from the past. The oxygens, if they need 3 regions to put electrons, that's Sp2 hybridization, right? Anything based on the trigonal planar structure with 3 total electron regions, needs 3 hybrid orbitals. So we hybridize the S and 2 of the P's. Okay, so I could add into this little drawing, let's put the lone pairs in 2 of these hybrid orbitals. The third, oh, you see where this is going, right? This guy and this guy are going to form the double bond with carbon. Wow, this is beautiful. We had said that like a double bond is the overlap of a sigma, an end-to-end, and a pi bond. Pi bonds are parallel bonds from the overlap of like unhybridized p orbitals. Bingo! That's what we have left. Here's the valence electron structure of oxygen. We've got the 2 pairs and the 2 singles. This is glorious. One of the singles is in the extra hybrid orbital, and the other single is in the unhybridized p. Those guys are going to overlap with carbon and form the double bond. You're getting this, isn't it? Starting to click. You're probably so proud of yourself. Okay, so let's start putting this together. Here are the sigma bonds. The carbon in the middle has sp hybrid orbitals. The carbon in the center is linear. And that's what creates the 180-degree linear bond angle around the carbon. The other sigma bond comes from the overlap of the oxygen hybrid orbitals. Okay, so in here we'll have 2 electrons being shared, spinning in opposite directions. These other hybrids around oxygen get the lone pairs. And again, they're trying to show this in 3 dimensions, which is a little tricky. These bond angles are the 120s. Okay, so when they ask me how many sigma bonds, and I think about my original Lewis structure, and then again we'll just put the dots on. Boop, 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 boop. Sigma bonds are overlapping orbitals, so we're not going to count the orbitals that have the lone pairs. Those aren't overlapping orbitals. There are 2 sigma bonds. 2 sigma bonds. They're right in here. 1 and 2. Those are the sigma bonds. The overlap of those hybrid orbitals, like kind of end to end. And again, I always knew that a double bond was supposed to be a sigma and a pi. Except there's 2 doubles, there should be 2 sigmas. Here come the pi bonds. Oh gosh, again, I love this picture. It's a little confusing in black and white, so check in your textbook if you want to see it in color. You can color code it in your study guide if that helps. Let's put some of those dots in that we had on the last structure. Here are the lone pairs. They went in hybrid orbitals. La la la, hybrid. Okay, I'm gonna kind of sneak them in down there. That green thing is the extra p orbital on oxygen. Then in here we had 1, 2 electrons being shared. 1 pair of electrons. La la la. There were the sigma bonds. The overlap of the hybrid orbitals. And now the carbon, again, if he only hybridized an S and a P, the carbon had the 2 unhybridized p orbitals. And each oxygen also had an unhybridized p. The oxygen was sp2, so we hybridized 2 of the p's, but we still have 1 unhybridized p. Can you see the 2 double bonds? Gosh, they're beautiful. And again, it's kind of tricky to put this in 3 dimensions, but we've got this guy. I'll kind of use red. So here's this p orbital, unhybridized p. He's going to overlap with this unhybridized p on carbon. And so we don't know if it's in the top lobe or the bottom lobe, but each of these unhybridized p orbitals has another electron. So when they kind of smush, again, they'll bend in toward each other so that all four lobes are kind of overlapping. Somewhere in there we're going to share a pair of electrons. So I might just kind of draw it in here. 1, 2. There's your double bond. The sharing of 4 electrons. 1 sigma and 1 pi. The pi bond will also have a pair of electrons. They don't really show it, so we'll just kind of sketch them in space. Even though, like in real life, those unhybridized p orbitals will like bend toward each other so that the lobes can overlap. And then the same thing will happen on the other side of town. Oh, what color should I use here? I might just go black. Okay, so here's an unhybridized p, and here's an unhybridized p. These guys are going to overlap parallel to each other, and somewhere in here we're going to share another pair of electrons. There's your other double bond. Oh, cool. So in this structure, we should have a total of 2 sigma and 2 pi bonds. And that makes sense. A double bond is a sigma and a pi. Carbon had 2 extra unhybridized p orbitals. They can overlap with the unhybridized orbital of each oxygen. And that's where we get the 2 double bonds. Pretty wild, huh? Again, color code this in your study guide. It might help a little bit because you really have to visualize the angles of these orbitals and the shapes of these orbitals. But it really does make sense. It's a beautiful thing.